was telling you a convex mirror has a virtual focus. You see that the focus is not real. So whenever you do problems, if the focal length of a convex mirror is given, you will have to take it as negative. Crucial, very important. So if the problem is about a convex mirror, because its focus is virtual, even though the question says the focal length is 10 centimeter, you will have to take it as negative 10. And then I told you just now that a convex mirror can only produce a virtual image. Look at that. The object is there. And how many rays do you need to get an image? At least two, and you see there are two rays, and the rays are never going to meet each other because they go away from each other. You see that? After reflection, they go away, but you got to imagine that they come from a certain point where they meet. Of course, that point. And that's why you have the image right there. That's the image. So it's diminished, it's upright, and it's virtual. Okay. No question. Again, remember, it should be taken as negative because it's a convex mirror. It's negative 1 by 8, negative 1 by 10, and do you get negative 4.4? Okay, if we're talking about DI and you got it as negative.
It's 44444.
Yeah, 4.444, it repeats. DI is negative. What does that show? Shows it's a virtual image. Any distance that's negative, virtual. Anything that's positive, real. So it clearly shows, because of the negative here, that it's a virtual image. All right. And then you have to find the magnification. What's the formula for magnification? There are two formulas. The main formula is HI by HO, or negative DI by DO. Okay.
Why was the radius negative?
Because it's a convex mirror. Because it has a virtual focus and it has a virtual radius. Okay, so magnification is negative DI by DO. In this case, that's what we use. So be careful, it's negative. I forgot to put the negative first. I think I added it, yes. Negative 4.4. So you get a positive. Do you see that? If magnification is positive, that means the image is upright. Why? Where is the positive y-axis? Up or down? Up. See? Magnification is to do with the y-axis, isn't it? Distances are to do with the x-axis. Now I think you understand it. Unless you want to make it complicated, which you should not. If magnification is positive, it's along the positive y-axis, that means the image is just like the object, upright. But if you get magnification as negative, it's inward. I want somebody to tell me. High school, refraction, never heard of refraction of light? It's the bending of light when it passes from one material into another. That's all. Because as long as light travels in one material, it moves in a straight line, isn't it? But if it goes, like, for example, if it goes from air into glass, it's going to bend. But only bend once, and where? At the interface. At the surface that separates air and glass, that's where it will bend. In air, it will move in a straight line. Once it enters glass, again it will be in a straight line. But just the interface that will bend. Now we can explain the bending using an idea, an example of a car that's moving really fast. And overnight there was flash floods or something, and the road got washed away. You don't realize it. And you're driving at 75 miles per hour. That's scary. And you do not know that the tarmac or the concrete road has been washed away, and you're suddenly going to enter gravel or sand or mud or whatever it is. So that is a sudden change in speed of your car. Now, can't you understand that your car is going to go off the straight path? Which has been caused by the sudden change in speed. The same is true if you jam on the brakes really fast, it's going to change the direction, right? Same thing. So when you know that light bends, you know it bends because of the sudden change in speed as it goes from air, or one material into another, basically. And light has the maximum speed in air, which is 3 times 10 to the 8 meter per second. And in glass, there are different types of glasses, but on the average, the speed is 2 times 10 to the 8 meter per second. That's a big difference, isn't it? From 3 times 10 to the 8 to 2 times 10 to the 8, at just 1 point is a big difference, and that's why light bends. Are you getting what I'm saying? And the refractive index of glass with respect to air, it's always with respect to air, is 1.5. Did you understand how I get that 1.5? If you were listening, you would. Where did I get that 1.5 from? 3 divided by 2. So what's the definition of refractive index? The refractive index of any material is the speed of light in air divided by the speed of light in that material. That's it. So if you want the refractive index of glass, speed of light in air is 3 times 10 to the 8, divided by 2 times 10 to the 8, you get it. Okay, I just wanted to see how it works without you writing anything. That's why I was not showing, although it was all made. Well, that's the formula that I was talking about. Refractive index, the symbol is N. You know that C stands for the velocity in air, and V is the velocity in any material. And here is a table that gives you all the refractive indices. Vacuum, air is the same, it's 1. Water 1.33, glass, I told you there are different types. Small differences. Do you notice that? Okay, this is lightweight glass. I believe this should be 1.58. That's a mistake. So 1.58 can be 0.58, right? So like that. Diamond. Now this is one of the reasons, not one of the reasons, this is the reason why diamonds are precious. We are stupid. Because diamonds are made of the cheapest material, carbon. And carbon is what you get when you burn something, basically. Right? But the reason why we are, when anything shines, we are attracted to it. Gold shines, but diamond does not shine. Diamond sparkles. The difference is, shining is a surface phenomenon. Sparkling is an interior phenomenon. I'm going to explain it, but it'll take a few minutes. I'll get to that. Diamonds are not like gold. For a diamond, when you look at a diamond, it looks like there's light coming from inside diamond. That's sparkling. But when you look at gold, well, of course, it shines from the surface because it reflects the light. So gold reflects, diamond refracts. We'll get to that. Now look at the refractive index. A diamond is the highest. That is what gives it those astounding properties that make us get attracted to diamonds. We'll get to that. I'm trying to keep you awake and alive. We're telling you this. All right. Very important. There are 2 ways in which light can bend. First of all, here it's going from air into water. It's going from a less dense medium into a more dense material, isn't it? So it bends towards the normal. Watch it. Light was supposed to go this way. If the material had not changed, it would have gone straight, isn't it? Now you see that it doesn't go straight, it bends, but it bends towards the normal. You see, it's coming. This is the normal, remember. It's coming towards the normal. So whenever light goes from less dense to more dense, it goes towards, which means the angle of refraction is going to be less than the angle of incidence. Because it's bending towards the normal. But if light goes from, all right, it looks like the same figure, but it's not. Did you notice that this time the arrows are in the opposite direction? You see? So now light is going from more dense to less dense, and it goes away from the normal. Why? Because light was supposed to go straight. Oh, that was supposed to go straight, isn't it? And how is it bending now? That's the normal, so it's going away from the normal. Are you with me? So which angle is bigger? The angle of incidence or the angle of refraction? refraction. So that is it. And one of the most important laws, it says here, like ray bends towards perpendicular, bends away. Just notice that. And then one of the most important laws of refraction is called Snell's law. It's on top, Snell's law, which says that n1 times sine theta 1 is equal to n2 times sine theta 2. Probably here, okay. That is Snell's law, very important to do problems. N1 sine theta 1 is equal to N2 sine theta 2. What are those terms? What's N1? Refractive index of material 1, right? N2, refractive index of material 2. Theta 1, there could be some confusion there. Theta 1 is the angle in which material? Material 1. And theta 2 in material 2. I'll tell you where it could get a little confused as we go on. Now it looks like, there, that's so simple. Okay, it is. There was this, well, the picture is good, but try to understand that this lady will look really crazy when the man looks at her, because she'll appear to be completely compressed in this part. Look at this diagram. Because remember I told you that we are fooled into believing that light always comes from straight behind. Okay, take a look at this diagram. You can see that light actually goes from water into air, bends away from the normal and goes into his eye. He thinks that it's coming from straight behind, correct? So he will think that the foot is right at this point, isn't it? So that entire region, this entire region will appear to be like squished together, out of proportion. The lady will appear to be out of proportion. That's what refraction does. In fact, if you take a pencil and put it half into water and half in air, you think it's broken at the surface. Come on, it'll be displaced, isn't it? All kinds of phenomena due to refraction. Okay, we'll come to that. So that's Snell's law. I told you that. And then this is another reason, this is another thing that refraction causes. You know that out of the electromagnetic spectrum, you can only see a small part, extends from 400 nanometer to about 750 nanometer, right? 400 is the 400 nanometers the wavelength of violet, blue, and 750 nanometers that for red. On this side you have infrared, on the other side you have ultraviolet. Are you with me? But what is white light? White light is actually all the colors in itself, right? If you pass white light through a prism, you send white light through a prism, it'll split into its colors. Can somebody tell me why? Based on what we were talking about.
Does your own have different speeds? Or no?
Very good. Why do you want to change? I was just looking at,
okay.
Did you read it off? And I was happy to find that you did not read it off. Because each color has a different speed. That's why. If the speeds are different, the speeds depend on wavelengths. If the speeds are different, the refractive index is going to be different, isn't it? Yeah? Because refractive index depends on the speed. And what does refractive index show? It shows you how much it bends. So the speeds are different, so the refractive index is different, so the bending is different, so they all do not bend through the same angle. They bend through different angles, and this is what you get. Which one bends the most from this diagram on the right side? Which one bends the most? Violet. And red bends the least. So which one has the highest refractive index? Yes. Refractive index, so NV greater than NR all the time for all materials. Refractive index of violet is always more than that of red. That's why you have, this is called dispersion. Yeah. It's called dispersion. Splitting of colors out from white light into different constituents is called dispersion. And the figure on the graph on the left-hand side shows you actually the refractive index for each color, for different materials. How many materials can you see? 5 different materials, and are they all behaving almost the same? Yeah. All of them have their height. What is the angle of refraction in this case? 90 degrees. So for a particular angle of incidence in the denser medium, the angle of refraction becomes 90 degrees in the less denser medium, right? That angle of incidence is called the critical angle. So what is critical angle? Critical angle is the angle of incidence in the more denser medium for which the angle of refraction becomes exactly 90 degrees in the less denser medium. Okay, go ahead and apply the Snell's law at that point and write it down, somebody. Just write it down. Apply Snell's law. Go back a little bit and look at what Snell's law was and apply it to this particular case, and you will get a new formula. What was Snell's law? N1 sine theta 1 is equal to N2 sine theta 2. And you know, take this as air. Take this as air and take this as glass or water, whatever. Why am I saying take this as air? What is the refractive index of air? 1. Okay. Apply it, you get a brand new formula. I'll let you do it and then I'll write it. Do you get it? That's where we start from. N1 sine theta c now. Because theta 1 is theta c, isn't it? And what's N2? What's N2? 1. So I'm not going to even write it. And what is theta 2? 90. What is that? 1. So on the right side I have 1. Yes. Therefore, sine theta c is 1 over N1. Right? Very important formula. So you can find the critical angle of any material just by 1 divided by its refractive index. Go ahead. Find the critical angle for diamond. Anybody remembers what the refractive index is? 2.42. Okay. Find out the critical angle for diamonds. I'll tell you, I'll show you why they are precious. Well, diamonds are forever. Nobody knows. 24 degrees. Now, just for the sake of comparison, find the critical angle of glass. Refractive index is 1.5. Just for the sake of comparison, and you will see the big difference. About 42?
42.
About 42, and for water it will be 49. Good numbers to remember. Because water will be, the refractive index is 1.33, so if you take 1 by, you will get about 49. Okay? You remember this in your mind. You're not crammed, but just know. Diamond, you got 24, isn't it? 42, 49. Look at the next figure now. What is the next figure showing you? When the angle of incidence is greater than the critical angle, what happened? There is no refracted ray. Light cannot come out of that material now. Light is trapped in that material forever. Cannot come out. That's why it's called total internal reflection. It's an internal process. All of it is reflected. Surely these two angles must be equal. That is what fiber optics is completely based on. So if you have light, I hope, I'm thinking about what should I explain first. Okay, I'll explain why diamonds are precious first. Now, if you set the pass first, what is it? It's 70% here, isn't it, to pass? 60, 70. What if the government one day says, like, we'll bring down the passing percentage to like 40%? More people will pass, right? So if the critical angle is small, as in diamond, then more rays are going to be totally internally reflected. Because the second condition I gave you, I told you there are 2 conditions for total internal reflection. 1, light must be going from more dense to less dense. 2, the angle of incidence must be greater than the critical angle. The angle of incidence must be greater than the critical angle. Otherwise, there will be no total internal reflection. Now, since the critical angle is really low for diamonds, that means there's a bigger chance of the entering rays to suffer total internal reflection. Isn't that easy to understand? So if the gems dealer, actually when diamonds are dug up from the ground, crude diamonds are not precious. It's in the hands of the, what do you call it? The guy who shapes it, the cutter, diamond cutter, whatever, who shapes it and gives it those phases. You know what he's trying to do? He's trying to make it in such a way that no matter how light enters, most of it is trapped inside. So when you have diamond here, you look at it, light enters the diamond, most of it never comes out, so it looks like there is a brilliant source inside. Because all the light is trapped inside. That's sparkling, and you're attracted to it. And you say, I want to get one, hang it around my neck, give it to my girlfriend, and so on. You understand what I mean? It's carbon, but because of total internal reflection, it sparkles. That's it. You understood that? Critical angle and diamonds. Now, fiber optics, I think, is on the next. We got this formula already. That's something else. All right, let me explain that. When you are underwater, you see the whole world around you in an angle of 98 degrees, in a cone of angle 98 degrees. Poor fishes and poor water organisms. They always see the world outside. Actually, when you lie down, and if it's not water, what's the angle at which you see the world outside? You lie down here, you see it at 180 degrees, isn't it? Just to bring it to the right perspective. But if you're underwater, you see all of it is compressed to an angle of 98 degrees. How do you explain? What's that? What's this light ray that's coming from this tree here? It has to go at the critical angle. Because everything in light is reversible, remember? When it comes at critical angle, it goes at 90. Then when it comes at 90, it should go at the critical angle. Come on. And the critical angle between water and air is 49 degrees. Remember that? Okay. So this one comes at 49. So this person thinks that, they should have drawn this figure a little bit. This person thinks that it's coming from here. You know what I'm trying to do. Same thing happens from the other direction. This feet appears to be somewhere here. And so now you see that the whole world, although it's 180 degrees, appears to be inside 98 degrees. Finished. And so they've given you a picture of, look at it. It appears to be really compressed. That's the idea. Okay. Now fiber optics. Oh, this is just the tip of the iceberg. Actually, there are so many types of fiber optic cables. Step index, gradient index, with cladding and all that. This is just the basic idea that if light enters one end, see, even if this is 1,000,000 miles long, light will come out the other end. Man, that's brilliant. It's transparent. Optical fibers are transparent, but light will not go out through the curved faces. And another thing is you can curve it any way you like. That's why doctors are able to send a fiber optic cable through your whatever organ and send light from here. They are sure it's going to illuminate the part that it reaches. So as long as they can make a small hole, put that fiber optic cable, it can bend and go reach that point. So they send light through this, and they illuminate that part of the body, and there's no light inside the human body. You know that, right? It's scary. It's dark. They want to see it. So what they do is they illuminate it and get that light reflected through the same fiber optic cable back again to get the image of that part on a computer. And they perform the surgery without cutting open the part. Think about it. You got it? Bend it anyway. Light reaches 1/12 minus 1/35. That's 0.0547 centimeter. That's 1 by di. That is 1 by. I just want to make sure that's not di. That's 1 by di. So what is di? 1 divided by that. Okay. So di is 1 divided by 0.0547, which is 18.26 centimeter. Tell me this. Is this a real image or is this, the question doesn't ask you, but I'm asking. Is this real or is it virtual?
Real.
How do you know? Because di is, you can write it underneath, it's just write real. And just make sure you understand that. And then it says, will the image be upright or inverted? How do you find it? Magnification. What's the formula for magnification? No. Negative di by du. Okay. Negative di by du. So you put negative di by du, and you got negative 0.52 means it's inverted. Because if you get magnification as negative, it's inverted. Some places where you can easily get grades in this chapter, provided you don't confuse yourself with the signs and all that, you know. Calculations are easy. Okay. Magnification is negative di by do. 3 is negative di by 1.7. So I'm trying to make di the subject. And I get negative 5.1 meter, isn't it? That's di. And then take it and plug it back into that other equation.
It's not asking for F, right?
No, it's asking for the radius. So, but you have to find f and then. Oh yeah. First you have to find f, then yeah. So you go to 1 by do plus 1 by di. And then be very careful there, because when you substitute di, what it's negative, remember? Negative 5.1, so you got to remember that. And you get f as positive 2.55.
This one happens to be really similar to our distance of our object.
What?
It just so happens.
Is this a concave mirror or a convex mirror? Now, what makes you say that it's convex? How do you find out whether? Wait. You don't go by what you think. You go by mathematical rules that I've told you. How do you know whether it's concave or convex?
Not always.
Di could be negative for both. Remember, a concave mirror produces a virtual image. A convex mirror also produces a virtual image. Now confusion is setting in.
But it's concave.
Oh, hold on. Let's talk about di. Matt, you got it, right? Di could be negative for both. Because both concave and convex can produce virtual images. You don't go by that. What do you go by?
If it can produce the focus.
The focal length is positive. So it should be
Concave.
concave. The focal length is positive. Concave mirror. F is positive.
Concave mirror makes you look taller.
No, we cannot go this way. You go my way. If F is positive, then we'll come to that, actually. But go this way first. If F is positive, surely it's concave mirror. Agreed?
Yes.
Okay, now let's go to your track. A concave mirror makes you look bigger, correct? That's why you have it in an amusement park. Who wants to look shorter than you are? I would never go there. If it's a convex mirror, it will make me look.
Yeah, that makes a lot more sense with the idea. Yeah, but
1 by do plus 1 by do, that's 2 by do, isn't it? 1 by f is 2 by do, so do is 2f. Where's the object? Where's the object kept? It's kept at the center of curvature. It's kept at the center. Oh, anybody with me?
Yes. Because that's the radius.
You remember, for a concave mirror, if the object is at the center, the image is exactly at the center and inverted. Should be able to see that in your mind. No, the image would be at 2f2. di is do. If do is 2f, di is also 2f. Alright? M is negative di by do, that's negative 1. Negative shows it's inverted. And then, oh, sorry. All right, number 4 is your quiz question. Is equal to n2 sine theta r. So 1 sine theta I is 1.56 sine 2 theta I. Hold on. How do you proceed after that?
The angles on one side.
Hmm?
Get the sines on one side. Since, so it's like angle, initial angle over two.
You can use an identity.
I mean, there are at least two ways of doing it, so I want you to proceed in your own ways. Go, and let's compare the answers. Because I did not get the answer given in the textbook. That's another reason why I want you to do it. Maybe I made a calculation error, you know what I mean. See, this angle here is called the angle of the prism. It's a constant. Let's call it A. Why can't I write now? Oh my hand is touching. That's A. A is the angle of the prism. You know it's constant because it's glass or whatever, perspex, plastic, whatever. You can keep changing it. So for a particular prism, A is a constant. Got it? Okay. Then from the geometry of this, if we call this theta 1, and we call this theta 2, no space to write it there. We call this theta 3 and this theta 4. Saw the angles? Are you watching? Then we can prove that theta 2 plus theta 3 would be equal to A. Can somebody prove it? No matter how you send the ray, always when you add the two angles inside, you see theta 2 and theta 3, you should get equal to the angle of the prism. Can anybody prove it geometrically? Quick. You see a chord here, you see a quadrilateral here, do you? And you know that the sum of the angles of a quadrilateral is 360 degrees? Okay. And out of those, these two are 90 each. So it's 180. When you add these two, it's 180, correct? And so the remaining angle should be A plus this angle, which I call X. A plus X is 90. That makes sense? If you've been listening, you should. Total is 360 and those two are 90 each, 180. So what gives A plus X is what? A plus X is what? 180, sorry. A plus X is 180. And then look at that inverted triangle that you see there. Inverted triangle, I mean this one. Do you see that triangle? The sum of the angles of a triangle should be 180. And those two are what? Theta 2 and theta 3 are two angles, correct? And then X is what? 180. Now look at these two, then you see this is true.
You would solve something like that.
If you don't, I'm sorry. Okay. Because the right hand sides are equal, equate the left hand side, X gets cancelled, theta plus theta 3, theta 2 plus theta 3 is A. Alright, okay. That is a very important equation for any prism. Theta 2 plus theta 3 is A. And you will be able to do this problem using those equations that I gave you. One more thing. Can I apply the Snell's law at phase 1? Can you tell me how to apply Snell's law here? First refraction, tell me. What's Snell's law? N1. So you'll be talking about, what's N1? N1 is air, isn't it? Be focused. So it'll be 1 sine theta 1 is equal to, N2 will be that of glass, isn't it? 1.58 sine theta 2. I just applied Snell's law at the first refraction, that's all. Agreed? Will that give us anything? Yes. No. No, because nothing was given. All right. We're going to use that equation anyway. We're going to use that equation because we have too many unknowns. Don't we? But the angle of the prism is given. What's the angle of the prism? I want to break my head and die. What's the angle of the prism? Somebody said it. That's why I'm not going to die. It's an equilateral prism, so it's 60 degrees. Okay, is theta 1 given? Is theta 1 given? 45. So if you have theta 1, can't you find theta 2 from this equation? Go ahead and find it. Theta 1 is 45, so plug it in. So sine 45 divided by 1.58 is equal to sine theta 2. And please tell me what theta 2 is. 26.6. Okay, 26.6. Now use this equation, not this one. Can you find theta 3? Yes, okay. So now you go 26.6 plus theta 3 is 60, or what did you say? 33.4 degrees. Now can you use Snell's law back here at the second phase? And you get your answer.
Aren't they equal anyways? Is that one?
No. That's just because how I drew it.
Okay.
It'll be equal only at a particular case. If I remember, I'll tell you the next day. It's called angle of minimum deviation. Well, just I drew it symmetrically. That's all. Since I have no space below, let me write it on top. Okay, apply Snell's law. Be careful. At the second phase, when you apply Snell's law, what's N1? Yes. 1.58.
Because it's actually, technically, would it be N3?
No.
Right.
That's N1, N2.
It'll be N, well, because if we think of it as...
Carlos. Oh, wait. Don't mess it up. Look.
Okay.
Outside you have air.
Yeah.
Inside is glass. That's all.
Okay. Yes.
Only two materials.
Okay.
So it's N1, air to glass. Second case, it's glass to air. Yeah. Because otherwise you would confuse yourself and then it's tough to come out of it. It's like getting into a wrong marriage, I mean, that's exact. It is true. Once you get into a relation which is wrong, all your life is gone. Same thing, if you think straight and get that physics fact, straight, you get it. But once you get confused, I'm not saying you'll never get it, but it's a lot more tougher to come out of that confusion. Okay. 1.58 sine, what? What is the angle? Theta 33.4. Come on, I hope somebody is doing it. You got it? How many got 60.4? Hey, all those who got it can go. No. That's how it would be in high school. Did you get the answer? You can leave others stay behind. So we got 7 problems done, and we finished this chapter. Now, okay.